Welcome back everyone. Today we're gonna keep exploring the Calculus 1 course and we're gonna go over section 1.4, which is continuity. Just a premise, this will be mainly an intuitive definition. We will give some we will define some things, and I will show you some theorems. But again, if you're gonna go over this level in mathematics, you're gonna keep going. You're gonna end up in a course called real analysis, where you're gonna have a much different definition of continuity. So please, again, understand that this will be mainly an intro, and then I'll show you some applications of this very interesting concept. So why don't we start right away? Also note, I have changed my format. Now I have A4 paper, which is a little smaller, and I put it vertical. So if that helps you with understanding, please let me know in the comments. I just want to try things out so that I make it more intuitive to you, for you to understand. Okay, so let's start with our point one of the day, which is what is continuity? And we start right away with this question, which, I mean, it would make sense. Why would we care in the first place? So let's imagine right away we have two graphs, and so I'll just put them one beside each other. And let's say here we have some function that goes like this. Maybe, I don't even know, it could really behave anyway. It could wiggle as much as we can, and not necessarily, but we'll find out why. And then we have this function, which has a white hole here, we have a black hole here, or a full hole. Okay, and let's call this line, I try to make them I try to put them on the same line, not super easy, and we'll call this x equals a. So right away, what can we see from how what can we realize from how I drew the graphs? Well, the graph on the left, if you check when I went to draw it down, I didn't have to lift my pen except for doing the little arrows, which I like. They're just I just like their looks. You could do this, you could leave it with no, and I just like the look of the arrows personally. So so when I drew this one, I didn't have to lift the pen from the graph. You can see that. Try and draw this. You can see your pen will now lift from the paper. I could just, it's a continuous movement, right? And on the other side, on the right, you can see that, okay, I drew the arrow now, but here I had to draw this white circle, which we have already seen in limits, and this means that the function, if you can see, now going up here, we have another black circle. We have not another, but we have a black circle, and again, as I was saying, I tried to put them on the same line, because this white circle means if we take the value x of x equals a, we go up to the white circle and we try to see what the function evaluates at, which is this height right here. Well, this white circle tells us we don't really care about that value. It's not included in our function, so it doesn't matter. However, if we go up and we go up to this circle up here, this is full circle, so then we want to know what our output value up here is. So again, going back to our smooth curve, or not lifting the pen from the paper, we can just see that this side right here we could draw without lifting the pen. We can even draw the circle without lifting the pen. However, here we have to lift, go up here, and define the second piece. So intuitively, we can say that F, so these two, we'll call them both F, it doesn't matter. F is continuous. This symbol right here, CTS, just means continuous, it's just an abbreviation. If I can draw I can draw the curve without lifting the pen from the paper, or in this case more like the pen from the iPad. Okay, so I think this is pretty intuitive. You could see it pretty clearly. So why don't we go and definition? Let's try and define continuity more specifically, and using the tools we found or we described in the last couple of videos. Okay, so what I'll do now is I'll give you a definition, and then we're gonna apply this definition. Let's see. So a function, so it could be any function. We'll call it f, again, just the easiest name. It's continuous. Remember, this is an abbreviation for continuous. Let me remove this. At a number a, so in our case up here, at this number right here, x equals a, at a number a, if the limit as x approaches a of f of x equals f of a. Okay. Now what we're gonna do is define this last statement we did here. We're gonna just define it a little more. So f is continuous. Actually, let's do it like this. So f is continuous at okay, so just f is continuous, I think is fine. If okay, so we got point A. So let's go back to this idea right here. So basically this is saying if we can evaluate the limit and the function of that value as only one output which equals the limit. Remember, if we take the limit as x approaches a minus of f of x, or a from the left equals and this means if we take, let's go back to our graph, if we take the limit as x approaches a from the left, we'll get this value. Now if we take instead the limit as x approaches a from the right side, we will get this value. So you can see they're distinct. We talked about this. If you did not understand, I recommend you go check our last two videos. We talk about limits and we define them clearly. If you have any doubts, please just feel free to comment. I'll try to help you. So again, going back to our discussion here, we can see here that we don't have really any symbols on that a. So this means we're just trying to see that the limit must exist right here. And remember, we say the limit exists if it's not equal to infinity or minus infinity, or if the two-sided limits are equal. So again, here we could just say these two are equal, equals f of a. So the function at that point, at the value x equals a, will be evaluated at just one output. So here you can see we have 1, we have 2, we got 2 y values. So this means the function is not going to be continuous. So let's recap this, because there's another point we should make. That is that f of a is defined. Why? I'll show you in a moment after we define the types of discontinuity. So f of a is defined, so which could also say f is in the sorry, my bad, a is in the domain of the function f. Here clearly in this graph, the a is in the domain because it's right here. There's no asymptotes. There's nothing weird that we can, like, it's not a square root function where we cannot take the left values. If you don't know what the square root of x looks like on a graph, it looks something like this. Here we know square root x is not defined for x smaller than 0 or equal, actually not smaller. So it's only defined for x greater than 0. So if we took some value x equal a and that value was a negative number, then there is no function there. So there's not even a point defining continuity. So f of a is defined. Then we said b, the limit as x approaches a of f of x exists. So this basically means check that the limit as x approaches a of f of x, sorry, from the right, equals the limit as x approaches a from the left. Finally, I'll do point C. I'll try to squeeze it in here. Let me just make this a little smaller. The limit as x approaches a of f of x equals f of a. And you can see they are okay, wait, let me finish, then I'll go on with what I was saying. If any of these conditions fail, then f is discontinuous or not continuous at a. Now, what I was saying is you can see that we have defined basically we have this definition where this is the first step. But if we don't have this, we don't even need to check this part right here. So we can go in a sequence. We can say that point A implies point B. Sorry, not point A, but point A must be true. And if A is true, then we must check for B to be true. And if we see that B is true, then we can check for C to be true. If we have a function and we check our domain and f of a is not even defined, so if a is not even in the domain, there's no point checking the limit. We're just done. Same goes for, let's say now a is defined and we have b that does not exist. We have infinity. We have an infinite discontinuity. We'll see this very closely. No, there's not even a point on going on to checking point C, because we already know our limit is not defined. So let's do an example before we move on. So I'm gonna have a graph. Just give me 1 second to draw it. I like drawing graphs by hand because I think it gives a little more the sense of connection to what I'm doing. I'll show you sometimes graphs in GeoGebra or whatever, but I do that because those maybe are graphs that would take a little too long to make, and well, I don't want to keep you here all day long. I just want to make sure you understand the concept, and if I can do so without the need of drawing the graph, then I'll try to, but I'll still try to draw graphs so you can follow along. So here we have a question that asks us, where is f, sorry, let's call this f, this purple function, where is f not continuous? And this is our question. So what we do here, when you see a picture like this, first thing you do is go check those full points or the white points. Now, how many do we have? You can see we have 1, 2, 3 white points, 1, 2 full points. Now, there's not really an order to start when you're analyzing the function, but maybe you want to start with the value closest to the x-axis, so why don't we start with x equals 1? So at x equals 1, what can we say? Let's go back to our definition. So if is f of a defined? Well, you can see if we take the value x a equals 1, so x equals a equals 1, so x equals a was from up here. Maybe you're getting confused why I'm changing notation, but x equals a, so our f of a will just be f of 1. So this basically means evaluate the function, evaluate the height of the function at x equals 1. So we go check x where x is equal to 1, which is right here. We go up, 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 and then we evaluate this. Now, from our definition, is a defined? If, let's say we take, so is 1 inside the domain of our function? Try to think about it. Do we have an output for that 1? Well, the answer is no, because our point is white. So again, if a point is white, that means we're going up, up, up to this point, but we don't really care what's here. So in this case, f of 1, so f of 1 is not defined. Okay, now let's check the next one. So we go, we just move along this way, and the second thing we encounter are these 2 points. So let's check, and they are on the line x equals 3. So again, you might see there is some similarity between this or this graph here, oops, a little bad, this graph here, and this situation here. Well, is f of a defined here? Is f of 3 defined here? Yes, the answer is yes, because here we have a black point, so this means even if the output is negative, we're gonna take this. We're not gonna take this white point. So f of 3 is defined. We're not gonna write it for this exercise, but maybe if you're just analyzing for continuity, you might wanna check out that option, so you don't leave anything behind. What can we see? Well, we can see approaching from this side and approaching from this side gives us a different value, different height. So what does this mean? Well, it simply means that the limit as x approaches 3 from the left, different of f of x, is different from the limit as x approaches 3 from the right of f of x. And we're done. This function is not continuous. We don't even need to check this because we know our limit does not exist. We can actually say it here. This implies that the limit as x approaches 3 of f of x does not exist. So we don't even have to check the other one. Now, let's go on. Let's check the next point. Let's go back to the graph. You can see the next point after x equals 3, where we see some dots, is x equals 5. Now, x equals 5, what do we have? Is the function defined? Is x equal 5 defined? So f of 5 defined? Well, here, no, clearly. This, clearly not. Well, but this, yes, they're on the same line. So guess what? F of A is defined. We checked off box 1. So point A, we checked it off. Are the two limits going to the same place? Well, yeah, they are, actually, because we don't really care about this point right here. Remember, the limit can exist even if the function is not defined at that point. So yeah, the limits are equal. What is the problem here then? We have to check this third option. Third option are the limit. Remember, the limit gives us, follow along on the function, gives us this value right here on the y-axis. Now, the problem is our function is defined at this height on the y-axis. So you might knew this, but the limit as x approaches 5 of f of x is different from f of 5. And so at these 3 points, the function is not continuous. Pretty simple, you could say, so far. Let's move on. Now, we have section 3. We have types of discontinuity. Okay, so types of discontinuity, it's quite simple. You don't really need to remember terms or anything like that. It's just for you to make a mental picture, and so that you can recognize from the graph what the pattern can be, what things to look for. Now, the first one I'm gonna introduce you is the whole or removable discontinuity. Okay, so the whole discontinuity is really something we have seen in the it might have been the second video of the series, I am not sure. Anyways, let's define this function. It's really probably the easiest one to work with, unless the graph, because it could really occur in some really complicated graphs, some composite functions, weird stuff, but generally at this level at least it's probably the easiest to work with. I mean, the infinite discontinuity is pretty easy as well, but it requires maybe a little more one requires a little more limit tricks or like manipulation, and one is more like algebra, standard algebra. So let's define f of x. So f of x will have x squared minus 4 over x minus 2 if x is different than 2. Nice. So then we have down here we have 5 if x is equal to. So first thing we do is we see that we have a factorable component here. Actually, why don't I bring this down here so I can follow up on it? So we have a factorable component. Remember our formula, x a squared minus b squared equals a minus b times a plus b. In this case, we have x squared minus 4, so we can say that this is really equal to x plus 2, x minus 2 over x minus 2 if x is different than 2, and 5 if x is equal to 2. We're going to cancel the common factor on top and bottom, and we'll be left with x equals x plus 2 over if x different than 2, and 5 if x different than 2, equal to 2. I'm starting to mix a little the words. Okay, so, well, this is pretty simple. You can see this is just a graph of a line. So we're going to draw our straight line. So let's see. I'm just going to say this maybe is 2, and then we have maybe 2 and 4 and 5 we need as well. Okay, so let me redo this. 2, 4, and 5. 2, 4, and 5. Okay, so down here. So we said, let's define this first. So we see that 5, the function is equal to 5, so the height is 5 if x equals 2. So we do our full dot, and then down here we're gonna do a white dot. Why? Because, well, generally here we have that our line is not defined at x equals 2, and if we plug x equals 2 into this, we'll get that f of x, okay, maybe I should have not drawn it in purple, but fine, is equal to 2 plus 2, so we're substituting x equals 2, which equals 4. But we know 4 is not a height that's defined, so we know 2 is not in our domain of this section of the graph, so we just okay, bad picture. So what we'll do is I'll try to keep it the same, but kind of hard. This will have to do. Okay, so this is my line. There's not really much to do other than the fact that we can see that the limit as x approaches 2 is x of x plus 2 equals 4, which is what I was telling you. This is why we have a hole. But guess what? The f of 2 will be 5. So since the limit as x approaches 2 of x plus 2 is different from f of 2, then this implies that f is not continuous at x equals 2. Pretty simple. F of x, let's do it this way. Let me put the sign here as well. This is our function. And again, I told you this was probably the easiest one to work with because there's not really much to do. It's just manipulation and really pattern recognition. When you see these factorables, you wanna make sure you check them through early. They can really save you a lot of time. Okay, so let's keep going. 3.2, our second type of discontinuity is what we call infinite discontinuity. Discontinuity. Okay, so let's see another piecewise function here. We have 1 over x minus 2 if x is different than 2, and 5 if x is equal to 2. So again, the 2 does it. So I'll tell you right away, we have a horizontal asymptote at y equals 0. We'll define also horizontal asymptotes in the next lecture. And okay, so finally, we can look at some another example. In this case, what we do is we analyze this part here. Why? Because we can't really say anything about this. We just know at x equals 2, we're gonna have 5, just as we had it up here. There's not really any difference. So let's analyze this function, this piece of the function here. We know it's not defined at 2, so that should ring a bell in your mind, and this means we have to check the limits, the one-sided limits. We already know f is not defined at 2, but I told you before we could stop right there. So if this question were to ask you, is f not continuous at 2? Well, then you could probably say yes. I would still be careful because, well, in this case, it doesn't happen, but just give it a check. Try to plug x equals 2 in here. Make sure it doesn't come out to be 5, because otherwise they might be playing tricks on you. But again, if they asked you if the function not continuous, you could probably most likely say yes right here without no need of doing any analysis. I'm just showing you how you would have to do it to prove why you're saying this is not continuous. Well, yeah, technically this part of the function is not defined at x equals 2, but the problem is here you have x equals 2, which is defined. And remember, this is a unique function. It's all together. It's not like, this is not like it's its own thing, and this is not its own thing. They're all together. So this means, again, in this case, when you have a piecewise function and you have no factoring you can do, to be 100% sure, you want to go check the one-sided limits and see what happens. So let's check the limit as x approaches 2 from the left of 1 over x minus 2. Now, again, if you go check the limits videos, you can see that we talked about asymptotes, and here we don't have any sort of manipulation with algebra that we can do, because if we even try the conjugate method, we're just still gonna end up with x2 on the top and x squared minus 4 on the bottom, which does not help us at all. Now, what we do here is we use our mental trick. So we're approaching from the left, remember, so a value a little smaller than 2. So this means we'll try to substitute mentally here. We'll have something like 1 over 1.9 minus 2, or this could be 1.999, doesn't matter, as long as you see that you would be left with 1 over negative 0.1. Now, what happens, again, if you make this very close to 2, then down here in the denominator you'd be left with like infinitely many zeros as you take x very close to 2. And you should know that dividing by a small, like by a number that has well, no, this is wrong, but like dividing by small number like this will give you a higher number. Why? Because let's say this is 0.1, you'll have 1 times actually let's do 1 over negative 1 over 100. You can rewrite 0.01 as this, so this will become, you're gonna have to think that this one here just gets flipped around, so the 100 becomes your numerator, the -1 in your denominator. So here, down here at the end, you'll have like -100. As when you get the number very, very close to, still a little smaller, but very, very close to 2, on the denominator, you'll have something like this, but on here, down here, you'll have many more zeros, and you'll end up with like an incredibly large number here. So this means this side approaches -infinity. If you check this here, 1 over this, you'll have infinity, which means that you can draw the conclusion. You could have drawn it already, but let's be complete and check the left as well, that the limit as x approaches 2 of f of x does not exist. So this, you could say, let me draw a graph for you so you can visualize it. So we said, oh wait, let me just make it a little longer here. Ooh. See if I can get it straight. Yep. Okay, so these are, oh, no, very bad. Here, okay, these are my axes. I'll have 2, and I'll have a vertical asymptote. Again, check the latest video about, should be the latest video about limits, and the previous video, and you'll find it. So again, you know, at 5 we are defined, but we know our function behaves somewhat like this, which means our function is not continuous. Infinite discontinuity, because our function just approaches -infinity and infinity, so we don't have a continuous function. All right, so we can just conclude, we can conclude that g of x is discontinuous at x equals 2. Nice. Let's check another thing. Let's check this. All right, so we are gonna check jump discontinuity. Okay, so once again, we're gonna have a piecewise function, and discontinuity can even be a non piecewise function, but this just gives, this example is more it's more of, gives more the impression. So we have 2 if x is between 1 and 2, and 1 if x is between 1 and 2, and 2 if x is between 2 and 3. What are the differences between the parentheses? This parentheses mean we're going to take our endpoint 1. So again, here it's going to be 2. And this parentheses mean we're going to keep it out. Okay, so this time I'll draw it for you. Might be a little hard to visualize this one. So let's say we have 1. Maybe I can take a little more space. 1 and 2. And here, down here, we'll have 1, 2, and 3. 1, 2, 3. We'll go something like this. All right, so I think this could work. Okay, so what can we say right away? So we can say it's f defined at whatever a, we could say it's f defined at 1. Yes. Is f defined at 2? Yes. So the first thing is checked off. What do you have after? Let's check the one-sided limits. The limit as x approaches 2 from the left of h of x. Did I write g of x here? Oh, okay, there you go, g of x. Correction. Okay. So h of x will be equal to 1, because as we approach 1 from the left, we're gonna have wait, sorry, 2 from the left. We're gonna have 1 is just this, and for the limit as x approaches, let me go under the limit as x approaches 2 from the right of h of x. This is just 2. You can see it from the graph up here. Excuse me. And then, so from this, again, we can draw the conclusion. Remove this. The limit as x approaches 2 of h of x does not exist, and therefore g of x, h of x, g of x was the other one, is discontinuous at well, 2 in this case. There is this concept which you should probably know, which is the concept of continuous from the right or continuous from the left. Well, if we just look at this interval here, we can see that our interval for this section right here, our interval will be 1 and 2. So that means we do not include the 2. So if we take every other point other than 2 in the interval between 1 and 2 other than 2, we can include 1 because we have the square bracket. That means our function will be continuous from the left. Sorry, from the right. Our function of 1 will be continuous from the right. Now, if we add another segment down here, maybe a 0, like this, would the function be continuous? Remove this from your mind. Will this function be continuous? Of course not, because we have the jump. We would have the jump discontinuity. But if we just look at this segment, so if we restrict our view just to this segment, then our function will be continuous from the left in that segment. Now, is the overall function continuous? No. But if we check this segment right here, we can say that it's continuous from the right. I hope I didn't say left. If I said left in there, it's from the right. Okay, so here I got to the part. I got too early to this. I should have probably put another page, but it's actually perfect because we move on, and our section 4 is continuous functions. So this is a pretty useful section. Let me remove this. I'll be consistent with the rest. This is pretty useful part because we can restrict down our thinking, and again, we are gonna have a bunch of functions that we know already are continuous, so we don't have to check every time, and we can just apply our algebraic rules, limits, whatever that is. So the following functions, let me get everything. The following functions are continuous on their domain. Let me make this a little bigger. Okay, so what is continuous on their domain? So again, on their domain, why? Because if we take the square root, for example, okay, very bad graph, but it's just a sketch to make you understand. This will be f of x equals square root of x. If we take some value, so the domain of the function will be x greater or equal to 0. You should know this probably. if we take some x which is not in the domain, which is on this side of the graph, there's not really even a function defined, so there's makes no sense talking about continuity. So continuous on their domain, so we'll have polynomials, so anything of the form x to the third plus, actually let me write it more generally, maybe like a0x, okay, if I can, a0x plus a1, okay, a0 x to the 0 plus a1 x to the 1 plus a2 x squared plus dot 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 whatever up to a n x to the n. It's going to be continuous on its domain. Rational functions, so anything of the form, it could be like x squared over 4, x minus 2. Actually, this is a bad example because it factors out. It could be x squared plus 6 over x minus 2. It's going to be continuous except that x equals 2. And we have root functions. I just showed you trig functions, so sine, cosine, whatever that could be. They're all continuous. Inverse trig functions, they have a restricted domain, so it could be arctangent, for example, or arcsine or cosine. They're all continuous on their domain. The log function, so it's kind of similar to the root function. It goes something like this. This will be the y-axis, this will be the x-axis. If you take something in this side of the graph, there's no point really talking about continuity. Exponential, so anything e to the x, 2 to the x, something that usually goes maybe like this. Again, if you take some values down here, there's no point talking about continuity because the function is not defined there. So also, now we talked about this. Also, what can we say? Well, also, the function is continuous at a and c is a constant. So the two functions are continuous at a and c is a constant. Then the following are also continuous. Wait, let me move this because it's not in line properly. It bothers me. Okay, here. It's probably not gonna stay in line. You have to take it this way, I guess. Okay, so f plus g will be continuous, f minus g, so subtraction will be continuous, multiplying a c by a factor c will be continuous, f times g is continuous, and f over g is continuous if g of a is different than 0. Okay, so finally, so this means also that we have one operation or function left to define, and that is composite functions. So okay, so let's define it now. If f is continuous at b and the limit as x approaches b of f of g of x equals b, okay, then the limit as x approaches b of f of x composite g of x equals the limit as x approaches b of, okay, this might be a problem, let me make this a little smaller, f g of x, and well, this means that we can move the limit inside, have a limit, okay, like this, g of x will be equal to f of b, because already we said that this limit is equal b up here. Okay, so this is a pretty important theorem you should know. Could really be interesting to applicate this, because we'll give an example right away. Let's say we have f of x equals e to the x. These are our givens, and g of x equals the square root of 1 minus x minus 1 over x. Now, let's say they give us the limit as x approaches 0 of e to the square root 1 minus x, oops, a little too big, 1 minus x minus 1 over x. So e elevated to this monstrous power. However, what do we know? Well, we know that e exponentials are continuous functions on their domain. Remember, the domain of an exponential function is all real numbers. On the x, the range will be y greater than 0. So this really means we can distribute the limit over and start work with this function here, which we have to analyze. Why do we have to analyze this? Because it's the most complex. And remember, why can we do this? Because we have this theorem. So you can see that f of x composite g of x is just f of g of x. So what you would do, this is e to the x. So what you do is you simply take this function and plug it instead of the x. That's all you do, and you obtain this stuff right here. This is the composite function, and you can just distribute the limit over. Now, if you evaluate this limit, I'll give you to check. This should be negative e to the negative 1/2, which equals 1 over e, square root e. Okay. Okay. Now, let's go over our section 5, which is an application. So let's see application of continuity of definition. So again, I told you we're going to see some applications. Here we go. Our question is, find pretty common question. Find a and b in the real numbers such that f of x is continuous for all x's. For my pen stopped working. Come on. Okay, here we go. For every x. Okay, so let's see. We have f of x equals a e to the x plus 1 plus b, x plus 1 plus b. If x is smaller than -1, we have x squared negative ax plus 3 if -1 is smaller than x, which is smaller or equal to 2, and then we have bx minus 4 over x minus 1 if x is greater than 2. All right, I'll let you analyze this for a second. Okay, so what do we do? First thing we do, again, domain. What can we say about the domain just right now? With the factors, imagine those factors were some number which didn't change what we see. The domain, at the moment, we just need to be careful about this one right here, and this one will be x different than 1, but well, we know that our function will be this when x is strictly greater than 2, so our domain is not important in the sense that we don't have to worry about anything. So let's start with the first part. So let's check continuity at the various points. So when you see the interval, these intervals, it basically means we have some points like this on a graph that could look whatever, but we have some points like this, and this interval is shared. So what we're trying to do is find a factor here, a or b here or b here, that will make the function be smooth without, and that point be a single one, without the need of jump discontinuity. So check continuity at the points. So the first point we encounter is x equals 1. Let me move a little to the left so I have enough space. So x equals 1. So let's check the limit from the left. X equals 1 minus of f of x is equal to the limit as x1 of f of x, which equals f of x. And this is this is what we want. So this is what we want to have. So what we do now is we are going to evaluate the different pieces. You can see x and minus 1, the point minus 1 is shared between this section here and this section here. So we're going to evaluate the limit as x approaches -1 from the left, because we know this is defined when x is smaller than -1, and we're going to check the limit as x approaches -1 from the right of this function, because we know x is greater or equal to -1, and then we're going to equal them to each other and find the coefficients. So let's see, the limit as x approaches 1 negative of f of x will be the limit as x approaches oh, this is a -1, this is a -1, could slip, make sure it doesn't. So -1 left, here we put the signs here as well, and we have our negative. So here we have a e to the x plus 1 plus b. We just substitute -1 for the x. So we're going to have e to the -1 plus 1 plus b. You know that this will be equal to 0, so e to the 0 is just 1, and this is a plus b. Now you do the same, but you check from the limit as -1 approaching from the right, and on the right we have the function, so the limit as x approaches -1 from the right of x squared minus 8x, let me check, plus 3. Okay, so again, once again, we can substitute -1 in there, and we would get -1 squared minus a times -1 plus 3. So the -1 squared is 1. A times -1 will be -a, but we have a minus in front, so this becomes a plus 3. which is just a plus 4. Okay. And then now to find these, we just check AB. We just put them equal to each other. Remember, this is the evaluation of this limit from the left, and this is the evaluation of this limit. Let me finish writing. So this is the evaluation of the limit from the right. So we just equal them to each other, which means we'll find b equals 4. So realize we have not found a yet, and to find a, we're gonna have to check. This is -1 as well, missed one there as well. So to find the a, we're gonna have to do the same process for the limit as x approaches 2 from the left, and we want this limit to be equal to x approaches 2 from the right, and we want this to be equal to f of 2. Here I should have put f of -1. Okay. Now, so let's check the first one, the limit as x approaches 2 from the left. This seems like a weird letter. So from the left we have again x squared minus ax plus 3, which equals to 2 squared. I'm just gonna substitute right away. 2 squared negative a times 2 squared plus 3, and this will just be 7 minus 2a, and the limit as x approaches 2 from the right, this will be bx minus 4 over x minus 1, and this will just be 2 times b minus 4 over 2 minus 1. This will just be 2b minus 4, if I'm not wrong. Yes, so we have 7 minus 2a equals 2b minus 4. We remember from up here that we found b equals 4, so we can just substitute that in. We get 7. Okay, 7 minus 2a equals 2 times 4. 2 times 4 minus 4. We get 7 minus 2a equals 8 minus 4, which will just be negative 2a. This will be 4. So we bring the 7 on the other side. This will be negative 3. And this means that we'll have a equals 3 over 2. So we can conclude for a equals 3 over 2 and b equals 4, f of x is continuous on for every x. Okay, nice. Okay, so we're almost there. There's one more thing I want to show you today, which is the intermediate value theorem. So let's check what we've done today. We've gone through a lot. Intermediate value theorem, so part 6, IVT. Pretty important. You're probably gonna need this part. Okay, I don't know why it keeps doing curved lines, please. Okay. All right, so let's start by defining the IVT. So suppose f is continuous on a, b, and let n big N be any number between f of A and f of B, where f of A different than f of B, then there exists some number C in open interval AB such that f of C equals n. And this is it. This is our IVT. We defined it. And okay, so this can have very interesting applications. So what this is saying is basically, let's say we have a function which maybe looks something like this. Let's say we have this function which goes, I don't know, could go anything. Let me try to do this pretty smoothly. Okay, so let's say this function is continuous and we have some a. This will be my a, and we have some point b, and this will be my b. Now these two evaluated. Oh my god, I can't draw straight lines. These two evaluated at these points will be f of a, we'll call them f of a and f of b. Now if we take any value here and we in between that interval and we call it n, and we take a c down here. So again, suppose f is continuous on AB, we see it's continuous, and let n be any number between f of A and f of B, where f of A different than f of B. F of A, f of B, they're different. Any number n in the middle. Then there exists some number c right here. So let's say we take c to be this. Then there exists some number c, excuse me, there exists some number c in AB such that f of c right here is equal to n. So okay, no, I want to draw it in green. F of c, so the value evaluated at c will be n. And I think this is pretty weird when you first look at it from the theorem, but if you see a picture it becomes a lot more clear. Now this is a very interesting application. I'm sorry, I just don't want to use the same. We'll call this example 3 if I'm not wrong. This is example 3 and this is example 2. Perfect. So example 4 will be something that you see 100%, and this, I hope this can really help you understand the logic between this. So our question goes like this. So show e of x equals 2 minus x as at least one solution, one real solution. Okay, and this is more like a proof rather than an actual exercise, but let's start. So let's see. So we have our f e of x and minus 2x. So we can really rewrite this. We could rewrite this as e of x minus 2 plus x, just bringing them on the other side, is equal to 0. And that's the first thing we're gonna do. So let's so e of x equals 2x, 2 minus x, can be rewritten as e minus e to the x minus 2 plus x equals 0. Just bringing them to the other side. Now, let's say we have going back to our previous image, though, we have f of x equals e to the x. Let's take the function f of x to be what is on the left side, and let g of x to be 2 minus x. So what is on the right side of the symbol? Now, what we did here in this step was simply to say, well, let's go back to look at these. What do we say? That the subtraction of two functions is still that are continuous at a point A, and we know e of x is an exponential and 2 minus x is a polynomial, so they will be continuous on their domain. So that means if we take the subtraction of those, what we get is continuous. And wait a second, our theorem says we need a continuous function. So we just found that if we take e of x, if we take f of x, which is e of x, and subtract 2 minus x, which is our g of x, we'll get e of x minus 2 plus x. And this is exactly what we have up here. So this means, so we have h of x, which equals f of x minus g of x equals e to the x minus 2 plus x is continuous everywhere where on its domain. Okay, and this is good. Why? Because we need a function that is continuous. This is the first point. Now, how do we find real solutions? We have I wrote you this because solutions to an equation come, we have to equal it 0 and find a solution. Now, the easiest way to find the bounds is to just search for a number that will make this this equation smaller than 0. And in this case, let's say for x, for a equals, for example, 0, we get h of x equals e to the 0 plus 2 plus 0. You know, sorry, minus 2. That's why minus 2. So you know that e to the any number elevated to the 0, it's just 1. So this is negative 1. And this is smaller than 0. Okay, so this is a good point. Our first bound a is that. Now, we search for a value b, which will, in this case, I'll tell you is 2, for which h of x is greater than 0. So we'll have e squared minus 2 plus 0, which equals whatever, but I'll tell you it's greater than 0. Sorry, actually this would be 2. These two get cancelled out, so this will be e squared, which is greater than 0. So now we have basically, so we have here, we'll call this f of a, which is smaller than 0. And we have our f of b, which is greater than 0. We know the function is continuous. So what does this mean? Well, this means if the function is continuous at a one point, which in this case could be x equals 0, maybe it's better if I write, well, no, it's fine. I'll just say a equals 0. In this case, we'll have, so I say a and b because we want a closed interval. So let's check the endpoints of that interval. Okay, so we know that at a, so on this, our function will be smaller than 0. In this case, our function is greater than 0. So it's over the line. But we know our function is continuous. So that means we're going to have at least one point in the interval from 0 to 2 that is exactly 0. So the solution to the equation that we have up here. Now, do we know that point? Absolutely not. We don't know what that point is. However, we can conclude that then by IVT there exists some point actually let's call it c because it's more like a value in the open interval 0 2 with f of a smaller than f of c smaller than f of b. And this is such that f of x equals e to the x minus 2 plus x as a solution f of c equals, so let's just substitute c, e of c minus 2 plus c equals 0. Boom, and we're done. This is it. This was the exercise. Pretty simple, yet pretty confusing at first. And yeah, and really we can use this to prove anything. So if we were asked what show that the root of 2 exists, we could just say, well, so this, if the root of 2 exists, we could just say that c squared is equal to 2. So which means c squared minus 2 will be equal 0. And see the pattern now? We have c squared minus 2 and something like this equals 0. It's always equals 0. We know this function will c squared minus 2 will be continuous. That's c squared exponential minus 2 equals 0. So this one is continuous as well. Sorry, this would be a polynomial. So it's just x continuous on the domain. So we can just say that a function, whatever, f of x equals x squared minus 2 is equal 0. And then from there on, you just find a point that is greater, that gives f greater than 0, a point b that gives f of b, a point a that gives f of a smaller than 0, a point b that gives f of b greater than 0, and then you can just conclude that the square root of 2 must exist because we need a solution to c squared minus 2 equals 0. So this was everything I had for you today. Let's recap real quick. We talked about continuity, now lifting the pen from the paper when drawing a graph. We talked about the definition of continuity. We saw an example. Then we talked about all discontinuity, infinite discontinuity, and jump discontinuity. 3 different types of discontinuity up here. Not finally, but after that we talked about continuous function. I gave you a couple of statements. We talked about this. This is pretty important. You should remember this. Pretty useful example. We talked about application of the definition of continuity. I found this comes up very often in the courses, so you might want to be pretty comfortable by doing these piecewise functions. And finally, we talked about IVT, depending on your school, you could cover it or not, but I think this could be useful for some of you. All right, so this is all I had for you today. I will see you next time, and we're gonna talk about asymptotes, horizontal asymptotes, and limits at infinity. Thank you, and bye bye.